In this section, we'll talk about inverse trig functions. Now, inverse trig functions are not the same thing as reciprocal trig functions. Reciprocal means you flip numerator and denominator. Inverse trig functions we had actually talked about a little bit when we did the right triangle trig, which is if you have the ratio of, let's say, opposite over hypotenuse, and you want the angle that goes with it, then you take the inverse sine, or you take the inverse cosine if you have adjacent over hypotenuse. So these trig functions that are inverses will help us to find angles. There's some interesting things that go with them and some graphs that go along with them as well. So we'll graph the inverse trig functions as well. So let's say you wanted the inverse of the sine function. You know that you can find the inverse of a function by flipping the x's and y's. So we're going to start with that basic idea that the inverse of y equals sine x is x equals sine y. And so we might want to graph it. So let's say we took a look at y equals sine x. The sine of negative pi is 0, right? The sine of pi is 0. The sine of negative pi is 0. Negative pi over 2 is down the bottom of the unit circle. Remember, sine is the y-coordinate, so sine is negative 1. At negative pi over 4, I get negative root 2 over 2. Sine of 0 is 0. Sine of pi over 4 is root 2 over 2. Sine of pi over 2, so now we're up at the top of the unit circle. We get 1. 3 pi over 4, we're over in the second quadrant. The y's are positive, and the sine of pi is 0. So if we go ahead and flip the x's and the y's, now we end up with something here. Basically, all these numbers just copy over, except now they're in the x position instead of the y position. All right, so what does this look like? It looks like the x's go from negative 1 to 1. So they go from negative 1 to 1, and then the y's start here at negative pi, they end at positive pi, and so that might be reasonable to call pi over 2, and that would be negative pi over 2, negative pi. So in terms of points, 0, negative pi, that's right there, negative 1 pi over 2, and then negative square root of 2 over 2 is about negative 0.7. So negative 0.7, negative pi over 4, 0, 0. Oh. It's a speed bump going that way. And then what happens on the other side? Square root of 2 over 2 comma pi over 4 is right about there. 1 pi over 2 is over here. And then eventually it comes back to pi. So what I've done is I've taken my sine curve and I've switched it around. And if I keep going, it'll keep going like this, back and forth, back and forth. What is the issue? Well, there's a couple of issues. One of them is that this thing here is not a function. In other words, if I try the vertical line test on this thing, it's going to fail. It's going to pass through more than one point. So it's not a function. What I'd like to do is I'd like to restrict the domain of this so that I only get certain values out, and I want a couple of things to be true. First of all, I want it to go through 0, 0. Okay. I want it to be a function, so I want them not to repeat the y values. And I want to do it in such a way that I get one of everything. In other words, I want to be able to say, here is square root of 2 over 2, and you pop out a specific value for an angle that goes with the square root of 2 over 2, and I don't want any repeats. I don't want any ambiguities. I want only one y value for every x value. So what I'm going to do is I'm going to cut it like so. I'm going to cut the function up here and over here. So if I include only this part here, then that seems to satisfy everything. That thing over there is a function. It only assigns one y value to every x value, and it passes through the origin. So x equals sine y is a perfectly valid equation, but is not a function. So instead of calling it x equals sine y, I'm going to create a new function, and I'm going to call it y equals the inverse sine of x. And I'm going to graph it only so that I have that part from here down to there. So this will be 1, that's negative 1, max is at pi over 2, min is at negative pi over 2. So that's what we talk about the restricted values for sine. So the restricted values for the inverse sine are between negative pi over 2 and pi over 2. So we're only going to return values on that interval. We're not going to return values more than pi over 2 or less than negative pi over 2. And notice that the other thing that's important is that by going from negative pi over 2 to pi over 2, I maintain continuity. If I said 0 to pi over 2 and 3 pi over 2 to 2 pi, it would have similar effect, but this branch over here would end up being way off the top of my graph, and it wouldn't be continuous. So we restrict those y values to be between negative pi over 2 and pi over 2, then we call it the inverse sine of x. So notice that it's the right half of the unit circle. So because the sine are the y values, by using the right half of the unit circle, we get one group of positive y values, we get one group of negative y values. Why do we do this? Well, the idea is if I say the sine of an angle is a half, rather than there being two possible answers, there's only one. So sometimes the question will say, give all theta values for which the sine of theta is equal to 1/2. So if it says the sine of theta equals 1/2, give all values of theta, then you would give both of those. On the other hand, if the question says give the inverse sine of 1/2, the inverse sine of 1/2 is that place on the unit circle between negative pi over 2 and pi over 2, where the sine is a half, so I go back and I look at it, and the only one that works is pi over 6. 5 pi over 6 is beyond pi over 2. It's more than pi over 2. All right, we already graphed it on this restricted domain. So find the inverse sine of negative 1/2. So where on my unit circle is the y value negative 1/2 on the interval from negative pi over 2 to pi over 2? So it looks like it's right here. But notice that when I go on my unit circle, it says 11 pi over 6. Well, I'm not looking for 11 pi over 6. I'm looking for an answer that's between negative pi over 2 and positive pi over 2. So rather than writing 11 pi over 6, right, I'm not going to write 11 pi over 6. Instead, I'll write that as negative pi over 6. Right? So now negative pi over 6 is on the interval between negative pi over 2 and pi over 2. All right, the inverse sine of square root of 2 over 2, that's easy, right? You don't have to go backwards, forwards. It's right there in that first quadrant. It's at pi over 4. Right, inverse sine of 1, that happens up at the top of the unit circle. So up at the top of the unit circle is pi over 2. Ooh, it just makes it. Inverse sine of negative square root of 3 over 2. So I know right away I'm going to be in the fourth quadrant because it's a negative y value. Y value of negative square root of 3 over 2 is down here. But again, I'm not going to call it 5 pi over 3. I'm going to start from 0 and walk backwards. Walk backwards how much? A pi over 3. So walk backwards pi over 3, that's negative pi over 3. Right, inverse sine of negative 1, that's down the bottom of the unit circle. Again, I'm not going to call it 3 pi over 2. I'll call it negative pi over 2. Now, the inverse sine of 4. This is saying I want an angle whose sine is 4. But the sine can't be 4, right? Sine can only go between negative 1 and 1. So this thing is undefined. Right? Trick question. So you can't have a sine value equal to 4. So if you ever see something that says, find me the inverse sine of 4, it's just undefined. All right, if we can do it with sine, I bet you we can do it with cosine. So y equals cosine x. Let's fill in some values for y equals cosine of x. The cosine of negative pi is negative 1. Remember, these are now x-coordinates. So at negative pi over 2, that's down the bottom of the unit circle, the x-coordinate is 0. At negative pi over 4, that's also in the that's now in the fourth quadrant. So the x's are positive there. Cosine of 0 is 1. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 2, that's the x-coordinate at the top of the unit circle, that's 0. 3 pi over 4 is now in the second quadrant. That's negative x values. That's negative 1. So if I take y equals cosine x, I switch the x's and y's, and oh, look, I get x equals cosine of y. So I get negative 1, 0, root 2 over 2. Because again, if I want to find the inverse, I'm going to switch the x's and the y's. So here I am switching the x's and the y's. All right, so when I go to graph this, it's going to look similar to the sine function, at least in theory. All right, this will go up to positive pi. So there's your pi over 2. There's your pi over 4 and 3 pi over 4. There's your negative pi over 2. There's your negative pi. All right, so when I go to graph this, I'm going to have a -1 negative pi, so that's down the corner over here. I'm going to have 0 pi over 2, or negative pi over 2. I'll have square root of 2 over 2, negative pi over 4. I'll have 1, 0. And then I'll have root 2 over 2 pi over 4. I'll have 0 pi over 2. Negative root 2 over 2, 3 pi over 4, so that's about negative 0.7. And then negative 1 pi. So this thing comes up like this, around over here. And you can imagine if I kept this going, it would keep going like this. Essentially, it's just the cosine function flipped over the axes. So instead of the x-axis being where all the pi divisions are, it's now the y-axis, right? We switch the x's and the y's. So can I have some of that same logic that I did before in restricting the values for the sine of x? Except this time I'm going to restrict the values for the cosine of x. Again, I want something that includes zeros. I want something that includes all the values at least once, but yet makes this graph a function. So what can I do to make this graph a function? Well, the way is sitting there is not a function, because if you draw the vertical lines, they repeat. So let's restrict this. Let's pull the part that goes from here to here. And I'm going to take just that part of it, and I'm going to assign it a function. I'm going to call it y equals the inverse cosine of x. And that's going to be true for values between 0 and pi. So think of the top half of the unit circle, right? Top half of the unit circle, here's where your x's are positive, here's where your x's are negative. So by going from 0 to pi, you include both positive and negative values. You include a value at 0, and everything happens exactly once. So if I say, give me the inverse cosine of 0, then where's the cosine equal to 0? It happens up here. So you would only give me a pi over 2. You wouldn't give me like a negative pi over 2 or 3 pi over 2. You would just give me pi over 2. And so the idea is that you're going to have exactly one value that comes out of it. All right, so this is the stuff we already talked about. We're going to use values from 0 to pi. Okay, call it the inverse cosine. And on its restricted domain is just the piece that goes like this. Okay. So there's pi, there's 0, there's your 1, there's your negative 1. So it includes all the values from -1 to 1 on the x's, and everything is done exactly once. So again, let's find the following. It says, remember to answer with values from 0 to pi. So the inverse cosine of -1/2. So where is the cosine equal to -1/2? Remember, cosine are the x's. So if I pull out my unit circle, where's the cosine equal to -1/2? Well, I'm going to look over here. It's true that it's also going to happen down here, but that's not part of the restricted domain. It's up here. So it looks like it's 2 pi over 3. And that's it. That's the answer. 2 pi over 3. Inverse cosine of root 2 over 2, oh, that's in the first quadrant. That's pi over 4. Inverse cosine of 1. So where is the cosine of 1? It happens at 0. I mean, it happens at 2 pi also, but that's outside of our interval. Inverse cosine of negative square root of 3 over 2. So negative square root of 3 over 2 happens in the x's over here, but that's not on our restricted domain. So go up to the top here. Where does it happen? 5 pi over 6. All right, cosine is -1 at pi. Oh, look, another trick question. Cosine can't be -2, so this thing is undefined. All right, how about tangent? What's interesting about tangent? Well, tangent is the one that has those vertical asymptotes. So where do the vertical asymptotes happen for tangent? They happen at negative pi over 2, so we'll call that undefined at negative pi over 2. Tan of 0 is 0, undefined at positive pi over 2. Tan of pi is also 0. What happens at negative pi over 4? Well, at negative pi over 4, you're down here. Sine and cosine values are both the same, except one's positive, one's negative. So you're going to get a negative 1. At pi over 4, you're going to get a positive 1. 3 pi over 4, you're back to this quadrant over here. You get a negative 1. Over here at negative pi, you're going to get a 0. So now, I've got some values to fill in. But when y is negative pi over 2 and when y is positive pi over 2, there's no x's associated with that. What's going to happen here? Let's put some values in. We'll call that pi over 2, 0, negative pi over 2, negative pi. So 0, negative pi, okay, negative 1, negative pi over 4, so that's halfway in between, 0, 0, 1 pi over 4, and then negative 1, 3 pi over 4. Well, this is going to be tough to see without me filling in some of these blanks here. What's going to happen is that there's going to be a horizontal asymptote over here and a horizontal asymptote over here. And you're going to end up with a graph that comes down like this. And if I kept going, this would keep doing it over and over. Right up here, you'd end up with another graph that comes up like this. And down here, you'd end up with another graph like that. So you'd keep taking all of these things that used to be vertical and flipping them around and getting them to become horizontal. All right, we need a restricted domain for the inverse tangent. Well, here's the easiest thing. Just take the one in the middle. So we'll use that for our restricted domain for inverse tangent. So if I have y equals the inverse tangent of x, I'm going to have to restrict my domain to not include the endpoints. So don't include negative pi over 2, don't include pi over 2, but include everything else. And so what you essentially end up with is just a sideways branch of the tangent function that comes like this, down, and like that. So it turns out that this graph has two horizontal asymptotes, one at positive pi over 2, one at negative pi over 2. So that is the restrictions that I put on the inverse tangent function. All right, and this just explains it. Do they include the endpoints? No, because pi over 2 and negative pi over 2 don't exist. Right? So we call the function the inverse tangent of x. Again, this is only the right half of the unit circle, so it's very similar to sine, except it doesn't include those endpoints. All right, let's try a couple of these, and then we'll do the rest of it in a second video. So the inverse tan of negative 1. Where is the sine and cosine the same values but have different signs? That happens at 3 pi over 4 and 7 pi over 4. Well, 7 pi over 4 is our closest bet, except 7 pi over 4 is not between negative pi over 2 and pi over 2. So instead of going all the way around the 7 pi over 4, why don't I work backwards and call it negative pi over 4? Right, so now negative pi over 4 fits in between negative pi over 2 and pi over 2. Right, the tan of 0 is 0, so the inverse tan of 0 is also 0. What about the inverse tan of square root of 3 over 3? Where on my unit circle are the two values the same that would produce a square root of 3 over 3? Look right here. If I take sine and divide it by cosine, I get 1 over the square root of 3. 1 over the square root of 3, if I hit top and bottom with a root 3, becomes square root of 3 over 3. So you may have to get a little creative to figure out some of these tangent ones. Where is that? That's at pi over 6, and that's fine. That's within our restricted domains. But what about the negative? The one underneath it is a negative root 3 over 3. So now, where are they different from each other? Well, this point here reflect it over to the other side, you'll get the same thing, but no, that's not in our restricted domain. It's got to go down. So you're looking at this point over here. Square root of 3 over 2, negative 1/2. That'll give you a negative 1 over root 3. Rationalize the denominator, you get negative root 3 over 3. Again, the same issue, 11 pi over 6 is not on the restricted domain. So how do we turn 11 pi over 6 into something that's between negative pi over 2 and pi over 2? Well, instead of going 11 pi over 6 this way, go negative pi over 6 that way. Right, inverse tan of negative square root of 3. So it would have to be something that has the 2's on the bottom and has a square root of 3 over 1 like that, except one of them's negative and one of them's positive, and it doesn't specify which one. Let's see what works. This one up here would work, except that they're both positive. This one over here would work, except we're outside the restricted domain. How about we come down the bottom? At 5 pi over 3, I have a tangent of negative 3. But again, I can't write 5 pi over 3 because 5 pi over 3 is not on the restricted domain, so we'll call it negative pi over 3 instead. And the inverse tan of 1, that's first quadrant, that's pi over 4. All right, a little bit left to do. We'll come back and do that in a separate video.